I'm Kathy Buttle, and this is Dan Gillespie. We're with the NRCS of Nebraska. Dan is our no-till specialist. He's from the northeast corner of Nebraska, and I'm from western Nebraska.
You turn your mic on.
Oh,
Oh,
there you go.
right.
Mine on?
Hello? Now can you hear me?
Hello?
We can't hear you.
Yes, I'm on.
Are you on? Okay.
Try that.
Do you want me to start over? Can you guys hear me out there?
Testing.
Yeah, there you go.
Okay, I'm Kathy Buttle, and this is Dan Gillespie. Even though we come from the same state, we're about 8 hours apart, so we have to deal with some little different conditions. But today we're going to demonstrate for you the Rainfall Simulator and how that ties into no-till and soil quality. I found over the years that not too many producers care much about soil quality until they have soil quality. And when they see what their soils will do for them, they become very interested in soil quality. So the Rainfall Simulator looks at two indicators of soil quality, and that's residue and aggregate stability. And y'all understand residue, right? Residue is just the armor, the coating, the cover on your soils. It protects the soil from that dreaded raindrop. And as much as we all like rain, that raindrop acts like a little bomb. And that bomb hits the ground at about 20 miles an hour. It causes compaction in about 6 inches deep, and it can throw that soil about 2 feet in the air. And then because erosion, the first part of erosion is detachment, and it breaks those soil particles apart, it leaves them vulnerable to water erosion and wind erosion. So we're going to protect our soil with residue. The other factor in soil quality that we're going to look at is aggregate stability. And aggregate stability is just how well the integrity of that soil clod will hold together. So when that raindrop hits, it'll hold on the soil particles and organic matter and the microbes and everything that's in that little aggregate will hold its shape and keep it from washing away or the wind blowing it away. I like to think of it like this. As ag producers, our paycheck is laying out there in the field. Now, if you worked in town at the bank and they gave you a paycheck, you probably wouldn't lay it out there in the field and not protect it. First thing you do is put a roof over it. And that's what we're going to do with the residue. The next thing you're going to do is probably build a structure around it. Now, if you build a structure and it's just made of boards and those boards aren't tied together in any way, shape, or form, they're not very stable. And we're going to try to make our structure stable by increasing our organic matter. The microbes in our soil build that organic matter, and they leave that glomalin, they leave those polysaccharides, they leave that glue in the soil that makes our aggregate stable. Can I leave now? When we talk about water-stable aggregates, what's a water-stable aggregate? Look at the two little pieces of soil I have in my hand. And can you see some differences? Randy, can you see some differences?
Yeah.
Tell me what are some of the things you see.
This is like a tighter soil. This
Okay.
is a little more
Fine.
fine matter.
Yeah. This one's got some pore space in it. You can even see some organic matter, some roots, things like that. This is a living community. Those little microbes or those animals, that soil livestock in there is working. It's building habitat. They're feeding off of each other. There's a lot of things going on in here. And because of the way we have treated our soil, the way we have tilled our soil, destroyed that structure, this one has turned into a ghost town. Nothing's going on there. It's just those boards without anything tying it together. So when we put them in water, the aggregate, the water-stable aggregate, will hold itself together. And the dirt clod that's man-made, we've just compacted that together, held it tight with compaction. As soon as water hits it, it falls apart. In order for water, you know the old game you played when you were a kid and you're sucking up a soda in a straw, You know, it'll stay in there as long as you don't let water in it. You hold your finger over the top. Soil is the same way. If water's going in, air's got to come out. And in a lot of these dirt clods, when we put them in water, as that air tries to come out, it'll actually explode. The air pressure will push so hard it explodes. So this is, you can see right away, this is not a water-stable aggregate. What is this?
A water-stable aggregate.
Thank you, Alan. It's a water-stable aggregate. This is a water-stable aggregate. It's a rock to a lot of you, but to me it's a water-stable aggregate. In other words, water is not going to tear it apart very easily. Now, will it hold water? Katie, will it hold water?
Very
It's
little.
got some water on it. There is an attraction, a tension to water to this rock, this silicate rock. Since the rock is a negative charged particle, the water is positive charged, and there's an attraction. That tension or that attraction is measured in centibars. Those centibars are what a tensiometer, the soil moisture sensors in your irrigation systems that you go out and put these little tensiometers in the field. That's what it measures in, is centibars. The drier the soil gets, those higher those centibars are. Because as that tension gets higher, or it gets drier, that attraction becomes stronger and stronger. So these are some of the things that you need to know about when you're irrigating, or how soil moves through water. Okay, so I have this jar of
Gravel.
water-stable aggregates here.
That's right.
And how much will these water-stable aggregates, these rocks, hold? Not very much? Not very much. Okay, so if I was to pour a cup, show them that it were no tricks, it's a
Am
cup
I in
of
the
water.
cup side?
Yes. That's a
Okay.
private joke. When we pour this cup of water through and we let the water go on through, how much of that cup of water is going to stay in that gravel? Not very much. We never have a jar. Nope, we need that. This will be all right. It'll hold about a quarter of a cup. We get about 3/4 of a cup back. So that's about a fourth of what we poured through there is still attached to those soil particles. That leads us to available water holding capacities. I'm often asked about available water holding capacities because we all think whatever we put into our soil we get to use, and that's not the case. So when we you all know sand, silts, and clays. Sands hold a little more water, silts hold a little, clays hold a lot of water. But we pour that water in, and it's not like pouring it in a bucket, it just goes in there and sets until we need it. There are things that happen to it. So we pour this 5.2 inches into sand, 5.8 inches into silt, and 6.1 inches into clay, and the gravity flow takes out the first inches and runs them through the system. That's temporary water. So we get to that, after about 24 hours, we get to field capacity. So we've lost a couple inches just through gravitational water that goes on through our root zone. Then when we have about an inch of that water in sand, about 1.5 inches in silt, and about 2.5 inches in clay, is still attached to those soil particles. And they're attached strong enough that the plant can't pull it off. So that's unavailable water. So that leaves about 1 inch in sand, about 2 inches in silt and clay. That's all you get to use out of that 5 inches. Very, very important that you get every drop of water into the soil, because you're not even going to get to use all of what you're putting in there. And if you're losing some of it to runoff, if you're not getting it infiltrated, there's that much more you're losing. So we have what we call capillary flow. That's the other way water goes through soil. We've got gravity flow when it went through the jar, and now we have capillary flow as it's pulling it across. Capillary flow, if you've ever went to the doctor to give blood and they poke your finger and they hold a capillary tube, just a glass tube, up to the little drop of blood, and the blood goes up into the tube. They don't suck on it, there's nothing, there's no gravity pulling it down. The side of that glass is silica too, and it is a negative charged particle, and that's pulling that water molecule up. I like to play with water when you put it on a table and you just touch it with your finger, you can pull it along, that's that attraction. This is capillary flow. This towel has fibers in it that are negative charged and are pulling the water up through that pore space. Okay? So let's look at some of our soils, and Dan's going to show this, but with the Rainfall Simulator, but we're going to go through this a little bit first so you can see it through these jars. Remember when we were kids, we were told that if Grandpa used to tell us we have to go out and till them soils and get them fluffed up, get some pore space in them, get them light, so when it rains, the water can go in, right? Okay, so this is a conventionally tilled, I assume a silt loam here, from here around Salina someplace.
Yes, watch guys. As I lift up and let the air escape, the water comes out of the
Down.
down. Okay, it'll release faster. Cassie, that's my oldest daughter. Kathy said before that the air spaces, the pores in the soil have to be able to let air out in order for water to get in. That's a little mini demonstration of that.
So you've got this conventionally tilled soil that we fluffed up so we could get water to go through. We've poured it on there, and as you can see, the first thing that happens is those little raindrops, those little
Dan,
bombs, and
Point
we
out the water line on it.
Right here. Here's the water line, and this is capillary flow, guys. It looks very
Suck it
similar
through.
to the napkin in the pan there.
But we've torn those silts and clays apart, and the clays have started filling in those holes, those pore space, and stops that water from going through. And probably not a lot of you. How many of you have borders on your fields that'll hold this water like this so it doesn't run off? We don't have a lot of borders on our field, so the first thing that happens is it's like this and it just runs off. If you are fortunate enough to have a playa or a old buffalo wallow that water sets in, it'll set there until it evaporates, so you still don't get to use it. Okay, let's try it on a no-till soil here, or this is a prairie soil, but this is a soil that has some good structure to it. It's got some, there's some more water in another jar. Dan, we pull through.
Once more.
Yeah. There's some macropores in there, the earthworms and all the little critters that have opened that soil up. The aggregates are stable, they're holding their integrity, they're not falling apart, filling up that pore space, and that water's running on through. And that's what we need. We need, as soon as that rain comes, we need to have that soil ready to take that water. Another thing that happens is, as that goes through there, the water goes through the pores, through the capillary, or through the macropores with gravity, and then capillary flow pulls it into those aggregates. Now that's where those nutrients are setting. So rather than just washing through and taking the nutrients and leaching them down, it's just going into the pores and setting there with the nutrients. So it's helping holding on to our nitrogen too. Okay, let's try it with another little situation here. This is a conventionally tilled soil, but it's got that gravel layer in there. So we all know that as soon as we pour it in there, it's going to run right to that gravity layer, and that gravity layer has a lot of pore space, and so all that water is going to sit there, right? Right?
Well,
We got to have our raindrop.
raindrop deflector.
In order for gravity flow to work, it's got to be stronger than capillary flow. It's got to be stronger than that tension. So first thing that's going to happen is the conventionally tilled soil doesn't have a lot of pore space. It's holding on to the water. capillary flow, that attraction's holding on to it, and it's got to get strong enough, it's got to get enough water in there to go into that gravel layer. So even though you have a gravel layer and you've got a lot of pore space ready to hold out all that water, if you can't get it through that tilled soil, through that fluff, it's not going to do you any good. So let's try it on good soil with good soil structure. Remember, now we've got a soil that we've got some glue and some nails in and not just boards and lumber.
Once again, when you release, the air is able to come out, so the water is able to go in.
Now we've got room for the water.
Hold it up. The bottom. No.
I don't have enough hands, just a second.
I'll be right with you.
For you guys that don't know this was, Bud used to do this, and so he's very particular how we do this. But as you can see, it goes on through then. So you have to understand the relationship between the water and your soils before you can manage your soils. But that's what soil quality is all about. Soil quality, the definition of soil quality is its ability to function. And as ag producers, we need it to provide the nutrients and the water that that plant needs. And we can't do that if we don't have good soil structure. Okay, the last little demonstration I'm going to do, this is